In this example, we want to find the equivalent resistance seen by element 1. Ultimately, we want something that's an equivalent resistance, Req, such that if we hook element 1 up to this, element 1 can't tell the difference as to whether it's hooked up to a single resistance with this resistance value or this network of 3 resistances here. That means that we want to take out element 1 and find the equivalent resistance across these two terminals. So we want to determine the resistance, which I'm going to call Req, across the terminals of element 1. One thing you need to keep in mind is that the way that this is drawn over here, this looks like an open circuit, but it's not. You have to keep in mind the context of what we're doing. We're looking for a resistance across these terminals. You have to keep in mind what we're talking about when we say resistance. Resistance is a ratio of voltage to current. So what we're doing is saying if we apply a voltage across these terminals and determine the current, that'll give us the resistance. Req is the ratio of that voltage to that current. Alternately, if we flow current into here and find this voltage, resistance is still the ratio of this voltage to this current. So it's fundamental to this that we're assuming that the current is not equal to 0. It is not treated like an open circuit. Another way to think about this is that we can calculate the resistance by replacing the element that we're concerned with a voltage source and calculate the current. Then the equivalent resistance is going to be the ratio of whatever voltage we apply here to whatever current we calculate. We can do exactly the opposite. If we wanted to, we could replace the element with a current source, calculate the voltage, and still make this same calculation. So the opposite is also true. Now that I've reiterated what we need to know about resistance in order to make this make sense, let's go ahead and do our calculation. In this particular circuit, any set of loops that I draw will pass through only 2 elements. So for example, if I draw a loop around here, that shows me that the 3 ohm and the 6 ohm resistor are in parallel. If I draw a loop around here, that shows me that the 6 ohm and the 2 ohm resistor are in parallel. Likewise, a loop through here tells me that the 2 ohm and the 3 ohm resistor are in parallel, and all of those are in parallel with this resistance Req. So all of these elements are in parallel. I have a couple of different ways that I can calculate equivalent resistance for 3 parallel resistors. First, I can simultaneously deal with all 3 resistors. The appropriate equation is Req is the inverse 1 over the sum of the inverses of the individual resistances. So 1 over 3 ohms plus 1 over 2 ohms plus 1 over 6 ohms, and that turns out to be 1 ohm. I can also calculate an equivalent resistance by combining any 2 of the resistors and then using that resistance in another equation to combine it with the third resistance. So an alternate approach, I'll combine 2 resistors at a time. So I'll say that Req1 I'm going to claim is the combination of the 6 ohm and the 3 ohm resistors. So Req1 is equal to the product of the two, 6 ohms, times 3 ohms over the sum of the two, 6 ohms plus 3 ohms. That's 18 over 9, which is 2 ohms. Now to get the total Req, that's going to be the combination of Req1 and the final resistor, which is a 2 ohm resistor. So Req will be the product of 2 ohms, which is Req1, times 2 ohms, which is the other resistor, over the sum of the 2 resistances, which is 1 ohm. Doesn't matter which approach I use, as long as I don't make a mistake, they end up being the same thing.